We go to the next speaker, Nishant.
Yeah, I'm going to share the slides. Oops. Yeah, is it visible?
Yes.
Might start the video to
Perfect.
more visible.
You're also visible. Great.
Yes. Thank you for giving me the opportunity to give this talk, and thank you for staying till the end of the wonderful workshop that you've organized. Yeah, so I'm Nishant. I hope some of you at least are familiar with the title of the talk, The Shape of You. U is a when you study linear algebra, U is a pervasive symbol, occurs everywhere. For example, you do SVD, there's U and sigma and V. So there's U and there's V also. So we're just focusing on U. So this talk is about tensors, which are at the core of all deep learning algorithms, and probably more than that. And I founder of Note Labs. It's a platform to do research without any boundaries. And I'm happy to talk more about it. And yeah, so this thing covers a little bit of my screen. Yeah. So last decade or so, a new style of programming has evolved, or much more people have become familiar with it, and it's the inputs X, expected output Y, and there's this box which has these knobs, and it computes this output Y prime. Then there's a diff function which compares Y prime and Y and computes some error, and that is fed back so that you can tweak the knob so that the next iteration, the output is Y prime is closer to Y. At a very high level, this is what the principle behind learning. These are the programs that learn, and for formal methods community, it's the counterexample guided synthesis is the parallels there. So this new style programming has evolved, and we are okay. Yeah, and we are one software 2.0 is a buzzword, or is a lightweight term that's used to describe this whole paradigm, and consists of 4 independent pillars: annotator, the model generator, the model builder, optimizers, loss function, and each of them is a vertical, and you need to get familiar with each of them very deeply to write these programs properly and carefully and optimize them. The common link among all of these units are tensors. So vector is a one-dimensional array, matrix is a two-dimensional array. ND arrays or tensors, you can call them tensor, are the fundamental data structure that are used here. Essentially, like we do in constraint solving modeling, you take any object in the world, you smash it down to, say, Boolean. In this case, you smash it down to real numbers organized along different axes, so as an n-dimensional array. So you use this text or image or speech or other kinds of tabular data. You smash it down to this tensor format, and then your machinery, the model takes over, and then the learning happens through backpropagation, which is the learning mechanism. And NumPy is the most famous tensor library, the go-to library, and in the past 5, 6, 7 years, TensorFlow and PyTorch, MaxNet, and several other libraries have evolved and disappeared. They're pretty complex. Yeah. So on the left-hand side is this kind of program that we are used to, this for loops and if then else, and looking inside a dictionary and indexing it by array variable. The right-hand side are the programs which are seemingly homogeneous programs where input X, and it goes through a bunch of what are called layers, and then you get the output. Shifting from left side to right side is a huge learning curve. and a lot of people have made it, and this whole discipline that has evolved around software engineering plus machine learning. Okay, so so we are used to if, and as you don't see this if and in dictionaries here. So the principal data structure X, what is X is a tensor, an n-dimensional array, and it's what is changing across the shape of X here in this program. And as you can see, it's completely invisible. All you see on the left hand side is the line of X. You have absolutely no idea about what the shape, the length, the size, dimensions of X is. Okay, so very quick way. So it takes a little bit of while to get used to thinking about tensors, and because since you can think of the parallel being a list. A list is a fundamental computer science data structure. You add in, insert, you search over a list, you can sort over a list. These are the API that you need to be intimately familiar to work, use them in big programs. Similarly, tensor is like bread and butter, so you need to be intimately familiar. One way to look at it is that A is numpy.array with these 6 parameters, 6 values, and you can think of it as a tree where there are 2 dimensions, 2 levels in the tree. You pick the first dimension has 0 and 1 value, so it has 2, so 0 and 1. You go down, and then you have 3 values to pick, and then you get down to a scalar. Okay, so this is a tree-like view that you can keep to visualize what these tensors are. And this mental model helps you in many ways. Another way is that it's a function from indices to real values. So and then tree represents that. Okay, so I'm probably hurrying through this, but if you remember the tree, you can understand a lot of the talk. Yeah, so if you dive deep, like I said, list, it took us a long time to learn about lists and all algorithms around it. There's a similar API around these tensors, and this is just a snapshot of it, and you need to get familiar with it. And if you start learning stuff, you then encounter code which uses that API, and the code is weird in many senses. It uses these indices, so TF to transpose. TF is TensorFlow. Some tensor 0, 2, 1, 3. So transpose, you probably know in matrix, it switches dimensions. Here for an n-dimensional array, you try to keep 0 and 3 where they are, but 1 and 2 get swapped. So that's what this n-dimensional transpose does. And there's a disconnect between what you're thinking in terms of program and the low-level representation that these libraries are allowing. And that's what the great pain is about. And I'll suggest and that's what we are going to address in this talk. Yeah, so this kind of cryptic code is all over the place. All popular models are written in this format of using tensors, and right. Yeah. So now trying to understand this. So n-dimensional array, how do you represent memory? Memory is linear, so you need to flatten it. How do you flatten it? You choose these meta strides, right? First dimension, it goes like 32 steps ahead. Axis 0, for example, goes 64 bytes ahead. So if to get to the second row, you have to jump 64 bytes ahead. For the axis 1, if you get to the second row, you have to jump 32 bytes ahead. And for the innermost axis, so it's linearized, and there are these meta strides that are kept, the compiler keeps to help you when you do random indexing into the array. Okay, this is a very low-level representation, and the problem is that these libraries expose these low-level representation, as I showed in the previous slide, and that's very painful. Okay, so the gap on the left side is the computer, on the right side is your mind, and yeah, this is tree which is linearized tree actually, which the computer understands. On the right hand side, we think of these programs as axes. So the data is represented, is parameterized along these axes. B is, for example, the batch size, the number of elements you have, number of images you have, for example, that you're throwing to processing. Okay, number of sentences you have. T is the length of the sentence. If suppose you're doing NLP, the T is the length of the sentence, and D is the dimension of each word, the embedding. Okay, so you think of these programs as the BTDs, and you take this box-like structure and how this goes through the program. Unfortunately, when you write the program, you have to shift all the way to the left and manipulate things in terms of this low-level representation. What is in between are how do you get from tree to a compressed? The third one is BTD, which is named. It's a sort of linear tree, but the ordering, if some of you remember, BTDs is the ordered dimensions. Whereas in our head, these dimensions, there's no dependency among these. So shifting between these representations in our head is very hard for programs, and it shows there are many. It's a pervasive problem. I'll give some examples of people struggling with the problem. Yeah, so this is the talk, and I am trying my best to. Yeah, so understanding the representations and flaws in the tensor API, that's the thing, and in that context, how do to work with these libraries? Okay.
Nishant, we can't hear you.
Okay, it was for a moment. Now it is better?
Yeah, now it's good.
Yeah, okay. Okay. Yeah. So I think this is just describing what there's a linearized representation, and you can change the order of these axes to better represent these. Okay. So there are three broad problems. One is that these libraries expose, all of them expose, and probably the tradition is from NumPys, all of them have inherited, expose the low-level physical memory model and then the broadcast semantics. So traditionally, if you have to work with two lists, list one, list two of different lengths, there's a way to pad one, and then you can, put them together if you want to make a table out of those two lists, right? So different length tensors or different dimension shape tensors have to be combined, and that's where the broadcast semantics comes in. You broadcast the smaller one to bigger one. Unfortunately, that's a core thing, and the semantics doc is not precise, and it gives rise to very corner case bugs. And on top of that, this is a more generic problem. The tensor shapes, well, dictionary, if you're working with dictionary, which is deep, when you're writing program, if you want to, at some moment you want to access some variable 2 levels down, you really need to have the shape in your head. The problem is worse with tensor, where you really need to have the exact shape in your head to work with it. So those are three fundamental problems. I will, so first problem is because of this being tied to, here's this array which has 2 dimensions. The first dimension, I call it n2, size 2, the second dimension 3, okay? And then this is reshape, which rearranges the array, 3, which we write 3, 2. What we want is a transpose-like operation, where matrix get transferred. But what happens in memory, the output below, is it just change it. It produces a transformation that doesn't match with our semantic understanding. And if you understand the low-level encoding of a linear flattening of the tensor, we can justify this. But what the programmer wanted was to maintain this 2 and 3. So the 2 axes, on the one axis, there's 0.1, 0.2, 0.3. And when I transform it, I want 0.1, 0.2, 0.3 in a single row on a single column. So that fails to hold in the output. Okay, so you can't blame the library. You actually, the correct operation to use is transpose with with those weird indexes 0, 2, and 1, where 1 and 2 are swapped. But novice programmers make this mistake many times. This is sort of tricky situation with no good solution. Okay, so that's the first problem. The second one is broadcast. Like I said, if you combine 2 tensors of different shapes, it gets messy. So I have one tensor with shape 32, 1, second shape 32. Essentially, they are vectors. The first one is represented as a matrix with a column size 1. Okay, And when you do x plus y, the output that you get, and this happens in all the NumPy, TensorFlow, PyTorch, the output you get is of shape 32, 32 instead of just 32 or 32, 1. And what happens is that go into broadcast semantics. Essentially, the different size shapes have to be balanced somehow. So in the second y, the compiler adds 1 as the first index, and now both shapes are the same size. And now the indices need to match, so it converts into 32, 32, and the elements are repeated, and so you get this weird output. This is a corner case stuff, but they show up in very weird places. You write a loss function, and you don't know why your value has multiplied 100 times, and it's really confusing. And the third thing is about the shapes are latent. This is code from BERT, which is a very popular neural network architecture based on instance of transformers. And like you see, there's this cryptic code down. It's a dense layer, a fully connected layer, and there are these comments. Study. It's almost like variable declaration. You do B is batch size, F is sequence length, T is another sequence length, and my code will work over these. So query layer is a tensor which has shape B star F and N star H, the first and second dimension. And without these comments, it's almost impossible to understand this code or the details of this code. If somebody, I would say even the programmer who wrote it, comes back after 6 months, and there's so many versions of these transformers, it becomes very hard to actually understand what exact data is flowing. And then the jokes all over Twitter, and the APIs are already very common. So what we need is a very systematic way of specifying the shapes of these tensors and taking care of those shapes in the APIs. Okay, so that's the key point that take away from this. The people have been trying to write these shapes in ad hoc manner in the code because there's no systematic formal mechanism, and it's not very trivial to have a language that describes the shapes, as I'll describe. And plus, you need to the API should take care of the shapes, input and output shape, provide specifications. Yeah, and it goes. I call it when I was learning writing these programs for the first time. It's a tensor Mishri is what I call. I'll show that this program converts into one-line code if you have a proper notation to write shapes. Okay, so I think this is just repeat. Yeah, I don't know if there are questions. I can allow for questions in between, but if there is a quick question, I can. Is everybody following the talk? Okay.
Yeah, yes.
I guess no.
Yeah.
Okay, you feel free to ask a very any kind of question. Yeah. So
Nishant, this is Rahul here. Not a question, but rather a comment.
Sure.
I was also very, very angry with this absence of dimension specifications of tensors. And so when I made this c.dsl, all the tensors are explicitly annotated with shapes, and the compiler type checks that you are not multiplying a 1x1 matrix with a 10x10 matrix and so on.
Exactly.
So, like, I perfectly understand the sentiment here.
Yeah. It's a broad misery. It's not at the scale of a pandemic, but it is quite unfair. And this slide is the 2017 Stephen Hoyer Google. There's a Google Doc. He proposed shape typing. So yeah. From a formal methods point of view, it's a specification language for shapes which is missing. And once you have the specification language, you can have the whole formal methods machinery after it. You can do type checking. You can do static type checking. You do dynamic type checking. It can help you as a code assist tool. And the trouble is that nobody is in agreement on what the right language is and plus how to incorporate into it. So 2017, the second one is proposal. This is in PyTorch issues. Third one, tensor considered harmful. What he actually meant was that the API was harmful without, if you didn't have idea of shapes, and it was all exposing everything. All of these are very nice articles to read. Yeah, so no consensus on named APIs. So what you need first is naming the dimension. A dimension has a semantic meaning in our heads. So we need to call it B and T and D, and not just some dimension, anonymous dimension of size 20, okay, which is what most programmers do. And once you have those names, you need to incorporate those names in the APIs. It's not easy. These tensor libraries are huge, complex beasts, and they have autograd inside it. That makes it even harder. And so that's one of the reasons why people have resisted. It requires deep changes. Yeah, much more can be said about it. Yeah, and PyTorch added name dimension support, but a limited sense. And people have added syntactic sugar on top of, like Rahul was mentioning. In almost all cases, there are, tons of variants of tensor libraries, or people have had different variants to make their lives easier or for specific cases. Okay, in computer science, there are two hard problems. That's when I learned the meaning of this code. It's naming things and cache validation, I guess. We have enough formal methods, checkers on that. Yeah. So, okay. So some examples. So in papers on the right-hand side, when you read about convolutional neural networks, it's without going into details of it, you see figures right on the right-hand side. There's an image, and the input, and it's smaller, fatter, and smaller, and then it converts into a small vector, which you use to classification softmax at the end. Okay, so the code for that is on the left-hand side, left column, the forward function that I showed you earlier. And you just see x, there's no change in x, these weird layers. And then if you dig into, say, layer 1, self.layer1, you see this code, which is a parameterized specification, and it's almost impossible to figure out. You go down somewhere inside an end of sequential, there's a con 1 plus 1, and somewhere down below there's a block. A block is a parameter. Block is what the con layer is. So it's almost impossible to, there's this zero correspondence between the nice figure that you see in papers and the code. And this is extremely painful. If you want to, at a beginner or a later stage, if you want to change this code, it is impossible without writing the shapes of it. So this project started when I was trying to write a decoder, Hindi to English language translator very naively, and I copied some forward function from somewhere, and then I tried to change it. It was almost impossible. This slide shows some, what I had annotated it manually everywhere to make sense of it, and then I could modify it. Yeah, so that introduces TSLib. I think I've conveyed the huge pain that the tensor misery that everyone is going through, and there's no good solution here. And the reasons being complex library plus low-level changes and consensus. The consensus is a very hard thing in this world. So our goal with TSLib was to make the tracking specifying tensor shapes as first-class citizen in programs. And so for that, you need a language for shapes. And it lets us semantic closer to our mental model, okay, and integrated with Python so that we can actually use it, and works with arbitrary tensor backend. So you don't want to, tweak those libraries. Avoid deep integration. Just try to see if things can be done. And the library is open source. It's relatively old slide. The stars have increased much more. Okay. Yeah, and the insight is that Python is a dynamic programming language, but it allows these optional type annotations. You can write X colon something, and the program ignores it when running it, but the static checking is coming in slowly. So yeah, this is what instance. The idea is very simple. You have to declare the dimensions, and you have to track the dimensions, the shapes in the program. So, but you need flexibility. So you declare these dimension variables. Batch size B is the short name for it, and the size is 10. And you typically want to change the number, so you can keep it as a parameter too. And so essentially you declare these dimension variables, and that's the first choice that we made. Given that you have a mental structure of what dimensions you're going to use in this program. And generally, even for very complex programs, it's just a handful of these dimensions. Then your program just flows smoothly in terms of these dimensions. Okay, so there are multiple dimensions defined in one line. And now the same forward function looks a little bit different. It is more verbose, definitely, but now you can sort of scroll down from top to bottom. You X, B, 3, H, and W, height and width, batch. So these are images being passed in. B3 is the channels, and H and W. And the next step after the first con, you see that the channels increases 64, the height and width reduced by half. The next two layers don't make any change. In max pool layer, the height reduced by height and width half again. So you can only see that the height dimension, height and width are gradually decreasing, and the channels are gradually increasing. And you can have parameters and this and that. Right. So now there is some semblance to that figure that we saw in papers, and the code is much more semantically understandable. Yeah, this is still verbose. I don't want to write these symbols, and there's essentially there's a you have to define dimension data structure and allow to use in program. But these strings, I started writing just these strings, which are interpreted strings, which are just short forms. In terms of capital B, you write small. You can just write B3 HW even without commas, and all that is supported. And you can look up dimension variables and the sizes in the program and then use them later on. So you need a lot of flexibility, and TSLib provides that. Yeah. So again, I have to how it interacts with the API. There are more details there, but one thing that might be appealing is that now that you have symbolic shapes instead of height is variable h instead of 224, you can change 224 to 512 without changing your assertions in the program. So you want these programs also need assertions of shapes at different points, and so you can change. Assertions remain the same even if you change the size, and that's the obvious advantage of doing things symbolically. Okay, and so formally, it's a very simple. You would think that you need just the names, and these shapes are just tuple of names, but it's more than that. Like I showed in the convolutional network, you need to track the provenance, the how the shapes are changing. So there's this initial shape, and then that gets transformed. And to capture the transformation, you need some arithmetic operators, plus, star, and division, and there are a bunch of placeholder symbols. Maybe you don't want to specify a dimension for a particular operation, and so you can abstract away by an underscore. And so the huge set of APIs that I showed you to me can be just captured by these. I would just jump and say rewrite rules on shape tuples. Okay, and if you, I might need to explain. So for example, BTD goes to BD, the lowermost row. This is a reduction operation where you get rid of the dimension T, and this is a reduce. Maybe reshape view is NCHW goes to C, gets multiplied by 4, and the H and W get reduced by 2. So you can my proposition is that you can conveniently forget the API and just think of programs in terms of these lots of shape transformations. A lot of what is going on in these programs has just these rewrite rules in terms of these named symbols. And there's the star also, which represents a list of shapes, and you sometimes switch between an array of shapes to a tensor. Okay, so so now I'm going to just flash the advantages of having this. Yeah, so this is some code from GPT-2, which was OpenAI's one of the, again, if you have followed the hype, it generates fake scientific novels for you, and now very recently it generates code for you also. So this is a particular function from that, which is obviously very cryptic. And what's going on inside is that there are a bunch of shape transformation. BHTD goes to PTHD. There's a transform, there's permute there, and then H and D dimensions get folded together as H star D. That's all is happening, and I think almost everybody would agree that reading the lower representation is far more cleaner and obvious than you won't want to go back to the older representation again. Warp is the function that that there's a single function that we introduce at the program level to capture sequence of transformation. So these programs sometimes do just a sequence of transformation unary operators one after another. So you can just capture all of them in a warp operator. Okay, so yeah, and BERT, I
Nishant, sorry to interrupt. 3 more minutes.
Yeah, I'll just finish this. Yeah. So again, BERT, we managed to reduce 25 lines in that code, and it was this function just goes away into one line. Yeah, and how again the libraries understand indices. We have these name symbols, so there's a way of lowering the name symbols into indices and then evaluating them. So pretty standard compiler stuff. Yeah, and then there's the small step and big step semantics. If you have a sequence of transformation, you might specify not all the intermediate steps, but beginning and end only. And then you have to discover how to do the transformation, and then I came up with a bunch of rewrite rules how to do that. Yeah, so yeah, there are more details there, which I'm happy to discuss offline. Yeah, so the other side of it is that this first library that I developed open source, and there's very interesting social dynamics, and people find this interesting, and even though they may or may not use it, but they talk about it on Twitter, and comparison with other languages, and this library exists. You get citations and blogs. Yeah, so there's a lot of interesting stuff happened. And people have been using this library on and off. And there's a lot of, to get it used more, there are different dynamics than writing theorems. So I'm happy to talk about it offline. Yeah, so there's more to done, and again, now you have these shapes, and you can label them, and then you can do, if you have a label program, then you can do dynamic checking, which is also very useful in many cases. And so build this standing checker that is piggybacked onto the Python tracing library that checks these shape box. But yeah, you have to write these like this time. You have to write the specification before you can get them checked. Yeah, so the more details about how that's implemented, but standard compilers, it's nothing tricky. Yeah, and this is just Off-Note Labs is an open platform for doing research, and there's some old projects, but a lot has happened since then. And welcome. If you're interested, please ping me more. Yeah. So the summary: there's a disconnect between the memory model of tensors libraries and our mental model. And naming the dimensions and having a language for specifying these shapes is the link that is needed. And TSLib is an instance of doing that. And with examples, we're able to show that it's really, really useful. Adoption is still a pain. I don't think name dimensions are adopted unless they get adopted in PyTorch and TensorFlow. The tensor majoring will continue. So thank you. If you have any questions, I know I exceeded it, but yeah, 6 minutes. Okay, thank you.
Thanks, Nishant, for a nice talk. Yeah, any questions?
So, Nishant, Deepak here.
Yeah.
I think I understood a little more about your talk this time than the last.
Okay.
So just I mean, a thought. So are you, so once you do these type annotations, and I mean, you apply these transformations and stuff, can you, you mentioned dynamic checking, but can you also like prove some assertions about the code, like, the shape of some variable is this at this point?
Yeah, I mean, that is, I would say, standard. You can, you need, for example, these shape changing APIs are the rewrite rules that I specified. They're enough. You can construct an abstract domain which just propagates these shapes through the program. That is standard. When you have these meta operators like convolution or RNN, and you want to jump across that, that is where you'll have to infer the shape transformer, or somebody specify it for you. And once you have that, it would standard type checking. It will, yeah, I would say that it's Type checking here involves both shapes and values of tensor sometimes, so it is tricky. Some people at Google, I think, tried to build that. I don't know if they've published paper about it, but yeah.
Okay, but you don't plan to do it.
No, dynamic checker is yeah, the pros and cons of doing that. So I'm happy to talk more. Yeah.
Mm-hmm. Okay.
Yeah.
Thanks.
Yeah. So Nishant, I have one question. So
Sure.
selling a new notation is always a huge challenge because how to measure its benefits is not obvious.
Uh-huh.
So do you have any thoughts on how do you measure the advantages of formally measure the advantages?
Formally measure this. Okay.
So in terms of, there's so much reduction in lines of code, so many fewer bugs that programmers write.
Yeah. So I mean, I'm not sure by formally what do you mean, but
So like I said, there are people who use your notation write fewer bugs. I don't know how you measure that, but that's one possible way. Or
yeah. So this slide I had, I'm not sure you saw this. BERT is a large library which is used by millions of people in this world, and this is the initial implementation by Google. And I rewrote it using a TSLib, and there's several advantages. This is a very code reviewed, very crisp code there, and I managed to reduce from 200 to 175 lines. So that's I would say a significant reduction. And one of the key why it's possible was that because these multi-line functions, which were also cryptic, could be reduced into one line code. So I'm not sure if this partially answers your question.
it does partially answer my question. Yes.
But yeah, more formal ways of evaluating a specification languages. That's definitely a topic of research.
Yeah. If there are no further questions, thanks Nishant for a nice talk.